Okay, section 7.3, part 2, we're still looking at volumes of revolution. We're going to use a new method, and it's called cylindrical shells. So we're going to look back at the lateral area of a cylinder. Remember from our work with surface area back in geometry and some work here in this class, where we're looking at the lateral area, the blue part that goes around the cylinder. And to find that area, we unroll the cylinder into a rectangle where the height of the rectangle is the height of the cylinder, and the circumference of the cylinder becomes the length. And if I multiply those two together, 2 pi r h, I get the area of that rectangle that wrapped around a cylinder. For our cylindrical volumes, we are going to add our thickness, which will be our dy or dx, to get a volume from this. So let's take a look at one. So the region bounded by the curve y equals the square root of x and the x-axis and the line x equals 4. So a quick sketch of that gives us this. And we're going to revolve it around the x-axis to generate a solid. So we're going to revolve it around the x-axis, and we're going to get cylinders or discs that look like this. If instead I want to do this with a cylindrical shell instead of a disc method or a washer method, then I am going to take from my eraser, and instead of dividing it that way, I'm going to take a very thin strip and I'm going to rotate it around. And I'm going to rotate it, and that forms a cylinder with a very small thickness. And if I do a whole bunch of these cylinders, another one here, etc., etc., I will get the volume of the entire rotation by using cylindrical shells. It's kind of like a can inside a can inside a can inside a can to fill up the entire space with cylindrical shells. Let's take a look at what this looks like and how we're going to set up an integral for this. Oops, sorry, they had a picture there. All right, so there it is. And again, since I'm going to do my shells this way, I'm going to do dy slices. So I'm going to rewrite everything in terms of y. Let's go to the next page where I have some more room to write. So here's our same picture. So I'm going to use this thickness, which is a dy thickness. The radius of my cylinder, which I'm using for my cylindrical shell, is going to be y. And the length is going to be the distance from this line to the curve, y equals the square root of x, or x equals y squared. Again, when I'm using dy slices, I want to put everything in terms of y. So the height of this cylinder that I'm using for my shell is going to be this distance here. The distance from the axis to here is an x value that's equivalent to y squared. The distance from here to here is 4. So the height of any cylinder, no matter where I put it, is going to be 4 minus y squared. The radius of this cylinder is y, and the area for the shell is going to be 2 pi r h, which is 2 pi y, 4 minus y squared, times dy. I want to get some thickness there. And the whole thing is going to integrate as I move my cylinder towards the center, getting smaller and smaller, filling in my entire volume of revolution. I'm going to be going from 0 up to 2. So it's going to be the integral from 0 to 2. I'm going to put my 2 pi out in front, y times 4 minus y squared dy. So that'll be the sum of all of those cylindrical shells nestled inside one another so that I form the entire solid. So let's look at how we can calculate this. Here again is our formula set up. I'm going to work the problem over here. I'm going to pull out my 2 pi, 0 to 2. I'm going to distribute that first y. It's easier, I think, to work with a polynomial than a product. So 2 pi times the antiderivative, 2y squared minus 1/4 y to the 4th from 0 to 2. 2 pi times 2 times, plugging in my 2, 4, minus 1/4 times 2 to the 4th. All of that minus 0. So 2 pi times 8 minus 4 is 4 times 2 is 8 pi. And that's the final answer for finding the volume using cylindrical shells. All right, let's try one more together. The region bounded by the curve y equals 4 minus x squared, y equals x, and x equals 0 is revolved around the y-axis to form a solid. So let's first draw a sketch. This is a parabola that opens down, goes through 4 and 2. So it's going to look like this. Oops, sorry. And then we have our line, y equals x, which looks like this, and x equals 0. So this is the section I'm looking at. And I'm going to go ahead and erase what I don't need here. And I want to rotate this around the y-axis, so my cylindrical shells are going to be up and down. Now, one of the things that I do have to find is this point of intersection. So my shells are going to go this way. This whole shape is rotating around like this. So we're having it look like this. If I did discs, I would have to stop and start 2 sections. So I'm going to go ahead and use my cylindrical shells and work my way around this shape going from the top curve to the bottom curve. So the height of my cylinder is going to be this top curve, and I want a y value in terms of x, which I have, minus my bottom, which is just y equals x. So that's going to be my height. My radius is going to be just my y value from here straight out. Okay, and that y value is going to be found in terms, my x value just in terms of my x. I misspoke, I apologize. Let me back up. Our radius is going to be the distance from the y-axis out, so no matter where I put my cylinder, it's just going to be my x value. I do need to find this point of intersection because I'm going to integrate from 0 to wherever this is. So let's take a look at how I would find a point of intersection between 4 minus x squared and x. I could try to set this up as a quadratic, but I hope you can see pretty quickly that I can't factor that. So I'm going to go to my graphing calculator, and I'm going to plug this in and get a 0 for this parabola, or a point of intersection for these two. Pause a moment and see if you can get the value that will make 4 minus x squared equal to x. So we should have gotten x equals 1.561558. If you didn't get that, we'll talk about it in class. I also want to show you how to store this so that if you haven't done that before, you can use that value and store it to use at a later time. So let's think again about our cylinders. I need 2 pi RH. For this equation, it will be 2 pi times x times 4 minus x squared minus x. My integral is going to go from 0 to this 1.561558 value. Put my 2 pi in front, and then I'm going to distribute that x. 4x minus x cubed minus x squared dx. Sorry, didn't mean to jump that quickly. So here's the integral that I'm going to use. I'm going to go to the next page now. Again, they're showing here. I don't like that they rounded this to the third decimal place, because if we want my answer to be accurate to 3 decimal places, it's better if any number that I'm using internally is more than 3 decimal places. But plugging this into your calculator, we do get 13.327. So really that's it. We'll do at least one of these in class, talk a little bit about storing an X value that we've calculated from a graph, and then we'll do some practice problems together. The next few screens are going to be quizzes for section 7.1 to 7.3. We are going to do a quiz, so you might want to go back to this at some point to do a little bit of studying for that quiz. Oops, sorry, they're doing a little more work here than I did. Okay, so quick quiz, here it is. I'm going to scroll through this and you can use it later if you want. And that's it for today.